fundamentally, to change the speed of an induction motor, there are a lot of ways to do that. A lot of people have done research in 19th century, because as you know, the induction motor was discovered in 1887, 1888, and we are talking about 2018. So effectively 130 years this motor has been used. So there are different methods have been developed over the years, but in recent times the method which is used is based on inverter. So inverter, effectively inverter you can say is a in terms of block diagram, you can say it's a block diagram which shows the electronic circuits. In terms of the, so it's a power converter, you can say it's a power converter, it takes power in one form. It takes power in one form which is direct current. In the form of direct current, and it gives you the power, output power, which is in the form of alternating current. So alternating current, of course, you can say is the voltage as well as frequency, both can vary. Okay, both can vary. So for induction motor, what exactly we need is variable frequency supply. Okay, variable frequency supply. Why do we need variable frequency? So this comes from the fact that the frequency of the supply and the speed is related to these equations. That means the speed, which is the synchronous speed, which is 128 by P. So what it tells you that the synchronous speed is basically proportional to the frequency of the supply. Actual speed of the motor is slightly less than the synchronous speed, because maximum speed is up to 5%. So actual speed is close to the synchronous speed. So synchronous speed is proportional to the frequency. So you can change the frequency if you want to. So that's your, let us say that's your slip, and you get the torque speed characteristic something like this. So this is your torque, the starting torque. So your full load torque somewhere like that, this much, and this is of course your T pull out. So this is the slip equal to 0. This is the slip equal to 1. So this is your starting, and this is your synchronous speed. So if you now change the frequency, what will happen? Effectively the nature of the motor will be remaining almost constant. So you will have something like that, or you will have something like that, you will have something like that. So you will get different. Now you may say, why the torque is changing? Because when you change the frequency, what the motor or the driver does is that V by F equal to constant. Why V by F equal to constant? Why you need to keep it constant? This comes from the fact that we have the relationship between the voltage and the frequency, something like this. Voltage equal to 4.44 F N phi m. N is the number of turns, phi m is the maximum flux. So effectively you can say that phi m is V by 4.44 Fn. So if you want to make the phi n, which is the flux, pretty constant value, then you need to keep V by F constant. That's why the V by F is constant. So you change the frequency, you need to change the voltage. So yeah, that's why the torque also reduced. So what we see here is that the speed changes by reducing the frequency, and you can effectively operate in this region. So this is the operating region. So you can make the motor to run at different speeds. So that's the fundamental principle of driving the induction motor at different speed. So effectively, I will talk about the inverter, its construction, how do you do that, so that you get the idea behind this. Any questions so far? Okay. So for inverter, it's an electronic circuit. We'll show it what is inside. Input is in the form of DC, direct current. Output you get in the form of alternating current. Now you may ask that in reality, what type of DC power we are talking about? So you know all DC power effectively the battery, isn't it? So battery is the main source, but battery will not give you continuous power. So when you think of running something continuously 24/7, 365 days, you need to have continuous supply of power. And in this world, we get that in the form of alternating current. We do not get in the form of DC current. So this DC actually is not a pure DC. It's rectified AC. Okay? So we have alternating current, we rectify it, we make it into DC, and that DC is used. In some locality where, may not be in Australia, where the power cut is very common, the people have inverter at home where they need to have battery. So battery can be charged, and then when the power is cut, then you can use the battery to make the inverter. Okay, so first we will see single phase inverter. It may not be too much important for the running a 3-phase motor, but just that will be very useful to understand. So we may have single phase inverter, we may have 3-phase inverter. So for example, what exactly we are going to get? We are going to get basically this type of waveform, isn't it? Where we have got a plus, we have got a minus. The drawing is not very good though. It should be symmetrical. Okay. So that's what we want ideally. Okay? But the real life is not always ideal. Real life is practical. And we need to compromise with a lot. So if I say, you want this, but I give you, instead of this waveform, I give you like this. I give you like this. How many of you would be happy, and how many of you will be very unhappy? How many of you will be very unhappy? Can you raise your hand, please? Only one. Only two.
Really.
Huh?
Depends on the application.
I did not say the applications. I am just telling that is it the alternating voltage, if I give you, will be good enough?
Well, we're going to rectify it anyway, right?
No, that's the voltage I am giving you. I am telling you, okay, you want alternating voltage, I am giving you that. So only 3 of you are unhappy. So there will be, so 4 of you, 5 of you. Quickly raising hand. All of you are unhappy. Okay. All of you are unhappy. So then I tell, so in the first year or in the second year, somewhere, you have studied something called Fourier transform. So Fourier, in the year of 1919, so more than 100 years back, just almost 100 years, he came up with something that if there is any periodic waveform which repeats, so like this waveform repeats after a time t, okay, so t by 2. So the periodic waveform period t can be analyzed with the help of Fourier parameters. So the Fourier parameters will be like that: Vt equal to a0 by plus 2 summation n equal to 1 to infinity a1 sine n omega t. So the time is t. Now what does it mean? It means that I can analyze any kind of periodic waveform with the help of some. This is the DC component. So that means there is a, if they are having some kind of offset, that also will appear there, and some of sinusoidal component and some of cosinusoidal component. So if you want to express this, you will see this is like this: a1 sine theta sine omega t plus a2 sine 2 omega t go on plus b1 cos omega t plus b2 cos 2 omega t plus c. And now I say that I have given you a waveform which is no offset, okay, which does not have an offset. So that will be 0. And I am making it such a way that all these terms, they are going to be 0. Okay? And this is a perfectly odd waveform, because this side it will come like that. So f of t equal to minus f of minus t, which means that cos terms will all go 0. So I have ended up with a1 sine omega t. Aha! Is the sinusoidal waveform you got? What do you want? You wanted a sine waveform? I have given you a sine waveform. Mathematically I can prove that this is sine waveform. Isn't it? Should be happy. You do not need to go out of the class. You can enjoy it. Okay, so now question is, how can we make it close to that? Because this is not the waveform what we are used to, isn't it? So basically, this is the starting point. This is the crude alternating current. Later on, what I can do, if you compare that actual sine waveform is like that. Okay, actual sine waveform is like that. So what is the difference? The difference is here I am giving little bit more. I am giving little bit more here, but you want little bit more here. Okay, I can do that. What is the problem? I'll do like this, okay, and I'll give a little bit here, very little here. Okay, so we'll see how do you do that. So fundamentally, I need a positive, a negative, and it's a repeated. So the first circuit, what actually the designer they come up with. Let's keep that on. Designer come up with something like that. So you have a DC supply. Okay, so you have got plus and minus, your supply voltage DC, Vs, and after a long research, they come up something like this. So what I have used here I have used here 4 transistors. So the transistors are T1, T2, T3, T4. So there are 4 transistors connected in the form of a bridge. Each leg, so we can call it leg, each leg has got 2 transistors, kind of series, and the node point is the load. Okay, node point is connected to the load. So you are using transistors as a switch. Okay, so ideally these transistors, they are all used as switch. So transistor can be used either as a switch or as an active component. Okay, so if I just quickly tell you that what exactly I mean by switch. So if you think of the transistor characteristics, so transistor characteristics is something like this, isn't it? Something like this. So this region is called active region, where your VCE, IC, VCE is variable. So there is a lot of voltage drop across the transistor. But this region is cut off, this region, saturation, and this region is cut off. So if you see a transistor as a switch, so ideally a transistor behave like a switch. What does it mean? The switch has got, mechanical switch has got 2 states. One state the switch is on, okay, switch is on, allowing the current. Another state switch is off. There is no current flow through that. So this transistor can be used like that. One state the transistor is on, the current will flow. Another state transistor is completely off. And while we do that, the whole idea, if you think of this transistor switch, if you calculate the power loss, okay, if you calculate the power loss is voltage times current, isn't it? So if when it is on, if you make the voltage 0, so power loss is 0. When it is off, current is 0 because there is no current. Power loss is again 0. So the way you are doing is to make the power loss across the switch is 0. That's the whole idea, that it should be as switch. So then the question is that what type of device we will have. So there can be different devices we have. One can be BJT, one can be FET, one can be MOSFET, one can be IGBT. So then there is also MCT, GTO. So there can be many. So BJT, bipolar junction transistors, FET, field effect transistors, MOSFET, metal oxide semiconductor field effect transistors, IGBT, insulated gate bipolar transistors, MCT, matrix, actually it is switching transistors, I think MST, matrix switching transistors, GTO, gate random thyristor. All these devices, there are a lot of devices, but most of the device has got some positive and negative, and right now you have got only one device which is very popular, is the IGBT. So most of the inverter you will find that IGBT is the commonly used. Okay, there can be some other exceptions, but normally is the IGBT. Okay, so you have got 4 IGBTs connected like that, and then you have got their gate circuits. So this is your gate. So G1, G4, they are the gate, G3 and G2. So you have to give them a pulse to make them on. So this will be your some pulse. Okay, so you have some pulse coming from some circuit, control circuit. So gate pulse, you can call it gate pulse. So in this particular situation, what you want the current to flow, or the voltage, rather we say voltage to appear across the load, plus and minus for half of the time. Okay, you want for half of the time, half of the period, your voltage at the node A should be positive with respect to B. So how do you do that? You make T1 and T2 on. Okay? So if you make T1 and T2 on, so then what do you get the circuit? I might write it again, okay? Huh? Yeah, so the T1 and T2 you are on, so your circuit becomes like that. So your circuit is like this, isn't it? So this is your T2, this is your T1. They are ideally no voltage drop across the T1 and T2. So this is your voltage. So this is your output. Now because this supply plus here minus here, because this will be plus and this will be minus, isn't it? So plus will come directly here, minus will come directly there. So the voltage appear across the output is the supply voltage Vs.
Isn't it a bit smaller because it's across the transistors?
Yeah, so in ideal situation there is no drop, but in practice there will be some drop, so there will be some voltage drop, voltage less appear across the output. But ideally you think of that ideal switch. So when you do analysis, everything is ideal, but then when you verify, you see something is not coming as per your expectation, then you say, oh, okay, what is the problem? So you take the non-idealities into account. So everyone is happy with that? Now you got the output voltage Vs, so output voltage is equal to plus Vs. Okay? Now you switch it off. Now when you go to switch it off, you are in trouble. Why you are in trouble? Because you have got an inductor. You have got an inductor in series. An inductor is like lazy fellow. Okay? It's not like active like Subhas. He will tell, no man, I don't allow the current to change very quickly. You understand? So you're trying to switch off these two transistors, but inductor is telling, no, I won't allow this current to change. So what happens, if you do that, then the inductor, they will generate a voltage which is L di dt, and that's such a big voltage that can actually ionize the air. And you have seen that when you switch off some appliances at your home. You have seen sparking? Have you seen or not? Sometimes switch off. So that inductor voltage, L di dt, that can ionize the air. Ionized air means 3 kilovolt per centimeter. So if you have 1 centimeter air gap, apply 3 kilovolt, then you can actually ionize the air. Okay? So it can generate voltage. So that means some problem in my circuit here, which is not complete. What did I miss? So whenever you have got any inductive load, in and transistor based circuit, in power electronics based circuit, you must provide a path for inductive current to pass through. So all these transistors need to be saved. So I must have some freewheeling diode across them, which is anti-parallel diode. So in earlier days, this diode was not considered as a part of the package. But now if you buy transistors for inverter, this diode will be coming as a package. You do not need to add extra diodes. But earlier days you had to use extra diodes. Okay, I'll come to that, how this diode come into picture. But let us say I switched off, inductor was allowed me to switch off, and then what I do, I switch on T1 and T2 goes off now, I switch on T3 and T4. So if I now switch on T3 and T4, now T1 and T2 is off, so T1 and T2 is not here. Now coming is T3 and T4, so this circuit will be going here and coming there, and this part will be going here and coming there. Okay? So this is my second circuit when T3 and T4 is on. So this is my T3, this is my T4. Okay? So now your plus appeared here in the B. So now B become plus and A become, because of this, A become minus. So you got what you wanted. So your periodic wave, half of the time you got plus for A, then half of the time you got minus. So that repeats. Okay? So that's repeat. So you got crude type of alternating current. So now first thing I will say that how these diodes, they will come to help me. So this is D1, this is D3, this is D4, and this is D2. So let us say that I got a waveform something like this. So this is my voltage waveform, and then the current waveform, because of the inductive load. So this is my voltage Vt, and this is my current It. Okay. So current, because of the inductive load, current will lag the voltage by certain angle. Okay. So this is the, you can say this is my phase angle or power factor angle. Okay. This is theta. Everybody agree with that? What exactly we are talking about? Assuming the voltage is sinusoidal, but of course it is not sinusoidal, but current still can be sinusoidal. So we'll look into that. So now, if you see that this voltage waveform and current waveform, how do I relate into the devices? So the devices, ideally, it should be like T1 and T2 here, T3 and T4 here, T1 and T2 here, and goes on, isn't it? Okay? So let us start from this point. So this onward. We'll come back here later on when we repeat. So this part we'll take it here. So if you see now from this point onward, what exactly happening? You have given gate pulse for T1 and T2. Okay, T1 and T2. So this device T1 and this device T2, they are on. So your current is positive. So T1 is having current like this, T2 is having current like this. Load current is positive here, going from A to B. So from this point to this point, which are the devices on? T1 and T2, isn't it? Now when you come here, what do you actually like to see? When you come at this point, what do you like to see? T1, T2 should stop, and T3 and T4 should come into picture to conduct current. But T3 and T4, they can conduct current only in the opposite directions, isn't it? So current should be negative. But unfortunately, you cannot force the current to go to negative. Do you follow me? The current is still positive. That means the current is still flowing from A to B. But T3 and T4, they cannot be switched on because the current is still flowing in the different directions. So at this time, what do you think going to happen? The diodes. So the sum of the diodes will come into picture. So which are the diodes you think will help you at this situation? So your current is here. Current is in these directions. Okay. They will continue to flow in these directions. So two diodes will come into picture to conduct current to help you for this part. Which one? D1, D2? Which one? Don't just try one by one, because there are four only, two combinations you can have or four combinations you can have. I don't want you to have this combination. I want you to tell me that what exactly going to happen. So this is the current you are expecting to flow. Okay? So from this side you expect to flow, T2 goes off. So you cannot have there, isn't it? D2 cannot allow you to current to flow through that, isn't it? For diode, always the current will flow anode to cathode. So this current will now flow through this one, D3. Okay? So if D3, here this goes off, then D4. So D4 and D3 will come to conduct this part. You get me? So if you do not have these diodes, what will happen? This inductive voltage will abruptly force the current to zero and generate that high LDI/dt, and they will damage the transistor. Okay? So this part, D3 and D4 will conduct current. Now when you come here, the current becomes zero, and you give the gate pulse T3 and T4. Already you have given the gate pulse T3 and T4, but they were not on. But now they will be on. So this part till here is T3 and T4. So the current now become negative. So your current now will become negative. So current will flow. So you will have T3 going through this, T4 going through that. And that will continue till this point. Till this point. Okay? And after that, at this point, T3, T4 off. So T3, T4 is off here, isn't it? Off. Then here, current is still negative. Current is still negative. So now, you will see the current is still negative. So you will have D1 and D2. So D2 will come like this, D1 will allow. So this one will be D1 and D2. So that's the way so this basically, as you see here, so this is D1 and D2. So those diodes, four diodes which we have in the circuit, they are extremely important to make a smooth transitions of current and also without damaging the electronic circuit. Okay? So that's the circuit you will have for the single phase. Now I'll just tell another important thing. So for example, I analyze the waveform and I have got the expression of the voltage something like this. Let us say Vt is V1 sine omega t plus V3 sine 3 omega t. Okay, let us say Vt is like that. Now you may say, why you got that? I saw that I have designed my inverter in such a way that I have got the fundamental component and I have got the third harmonic. So I have got the fundamental and I have got the third harmonic. So I am asking you, tell me what is IT for the expression. So this V1 is the peak value of the so some people also call fundamental as the first harmonic, but we don't say the fundamental as harmonic, we call it the fundamental. So whatever you see in the world, the power is supplied by the fundamental component. So you can also call it first harmonic, but it's not the first harmonic. And V3 is the peak value of the third harmonic. So how do you get I for this waveform? This is like two sources, okay? You know, in the first year you did age 150 that if you have multiple sources in a circuit, you actually use superposition theorem. Did you do that? Remember? So what is the superposition theorem tells us? That you can actually analyze the response in the circuit due to one source by taking one source at a time, and then you superimpose all of them. Okay? Now while you do that, of course you say that the assumption is other source should be replaced by the internal resistance. Of course, if the internal resistance is 0, you can replace them by short circuiting, isn't it? So I have got two sources. One is the fundamental V1 sine omega t, another is the third harmonic V3 sine omega t, 3 omega t. So if my resistance and inductance is R and L, so this is R and L, how do you get the current? So let us say the IT is I1t plus I3t. Okay? So I add them. So I1t is the response due to the first or the fundamental, I3t is the response due to the third harmonic. So what is the I? What is the I? It's simple, isn't it? V by impedance. Okay? So what is I1t here?
T1 sine WT on the R and L back W.
So V1 sine, so you can say so here what will come? R plus
The frequency of that.
J omega L, isn't it? So that one you can actually write down like this. I1 sine omega t minus theta 1. Can you write like that? So what is I1 and what is theta 1? So I1 is how much? R square plus omega square L square, isn't it? Everybody agree with that? And what is your theta? 1. So tan inverse omega L by R. Okay? Everybody get back to that the first year stuff. Very simple stuff. So that's the fundamental component of current. But that's not that difficult. The second part is a little bit of difficult. Okay? Fundamental is not. So what is the second part? I3. What is the I3? So let us do this part here. I3. So what is I3? So I3 will be V3 sine 3 omega t by R plus J
3 omega T.
So 3 omega L. Okay? 3 omega L. So you have to take the frequency of the third harmonic. So third harmonic has a frequency 3 times F. So you have to take 3 omega L. So then it will be I3 sine 3 omega t minus theta 3. So I3 will be V3 by R square plus 3 omega L whole square, and theta 3 will be tan inverse 3 omega L by R. So what actually happened, as you go on increasing order of harmonics, as you can see here, the impedance go on increasing. Okay, so the current effect on the current will be much less. So even though your voltage waveform very crude in terms of alternating current, but your current will be much closer to sinusoidal. Okay, because of this fact that the impedance will not allow current for higher harmonics to flow. Do you get me? But this is of course not the voltage waveform you will see. You will see much better voltage waveform. So next questions for this is that, okay, so you may say that I can complete that. So I will write I1 plus I2. So here I write I1 sine omega t minus theta 1 plus I3 sine 3 omega t minus theta 3. So if you want to know how much is the RMS value of the current, these are the peak values. Okay, these are the peak values for any alternating wave. You have to take the peak value. So RMS value, of course, you have to divide by root 2. So if I ask you that what will be RMS for this, for each component you have to take, so you will get square root of I1 square plus I3 square, so on, and then you have to divide by root 2. Okay, so that's the RMS value you will get. So square root of I1 square plus I3 square and so on. If you have more than 2 components, then you need to take all the other components and you have to get the root mean square value. Okay, so that way you have to get this. So in practice, the waveform you generate is called PWM inverter. Did you hear PWM term? You have heard for switch mode power supply, isn't it? So what we go for inverter is called PWM inverter. So how do we get the PWM inverter? So PWM inverter basically same technique, PWM technique, but it is little bit different than DC. For DC, how do you generate PWM? How do you generate PWM for DC? Do you remember that PWM for DC? What do you do?
Turn it on and off really quickly.
How do you get that? Do you have any idea how you can actually do it in discrete circuit? So I need to have a frequency at which I want my device to be on. So that's the frequency you are talking about. Okay, so the frequency is 1 by T, and then I have a DC voltage. Okay, I better not to give AC here. So you may say, oh, it's already AC. No, it's not AC, it's DC. Okay, so let us say I have got a DC voltage, which is something like this. Okay, and I compare them. So you have a comparator. You have a comparator where you give the this you can say is DC reference. So this is your DC reference, and you got this one is called PWM carrier signal or carrier wave, whatever. So PWM carrier, and here you got a pull-up. So this is your comparator, which is called open collector comparator. Okay, open collector comparator, and you have got a pull-up. So this circuit, this comparator circuit, what it gives you? When your plus is higher, then you get high. Okay, when the plus is lower, you get 0. So you think of unipolar supply. Okay, so if I now plot my voltage, what do you expect I get here? What do you expect I get here?
Square wave.
Square wave, high or low?
So you start off low and you go
So-
high.
So when this is high, this should be high, so you get like this, high. At this stage, my signal is low, DC reference is low, so I get low here, continue up to this, again I go, isn't it? Go. Everybody follow me? So that's your PWM. So in switch mode power supply, you do. So this is fixed, this carrier wave is fixed, because usually switch mode power supply operate at fixed frequency. And that reference is actually coming from error amplifier. The error amplifier, they compare the reference voltage and the feedback voltage from the output, and they amplify it with a gain. So that comes from the error amplifier. So the error amplifier you compare with the PWM carrier wave. So that's the pulse you get. So if error, this goes high or low, your pulse width will change. Okay? If it goes high, pulse width will be high. If it goes low, pulse width will be low. So then you adjust the output voltage. So that's what you do in DC, switch mode power supply. But here we are talking about alternating. We want to get alternating output. So how do you do that? What you keep is the reference wave. In many situations, this triangular wave, they actually make in a different, so this part is alright, isn't it? So this triangular wave, they make a little bit different. So what they do is something like this. So we are talking about PWM pattern. So what they do, they actually do the triangular wave something like that. So the